Today we will be doing something. Yeah, well, another magic day. I'm sorry. We are going to take regression one step further. And it's a very important step that will take us towards what today is known as machine learning, big data, statistical learning, data mining, you name it, and is basically as important for our society today as the ability to be able to read a book. So, the ability to be able to understand how people mine you and predict you and filter you is at the heart of being able to be an intelligent citizen in the society today and in the future. And you guys need to be on top of that, because if you're not, who the heck should be on top of it? So we need to be on top of it. This is not a machine learning course. You will see that you could take machine learning courses. Even the definition of what is machine learning and what is statistics is pretty blurry. And different people will give you different answers. Machine learning is in a way the same as statistics in many ways, but in a way that's what people call it if they think about those tools that people in computer science started using, which, by the way, are the same tool that people in statistics used for 100 years. But of course there is a new situation today compared to 100 years ago. So for sure, new things are happening to us in terms of available data. But you can take a machine learning class and you'll learn about regression and linear regression and extensions. So that's why this is an important day today in our basic stats class, to be able to do what is known as multiple linear regression. We will warm up a bit with familiar items from last time. We will split around here and discuss why we, of course, need to go on from where we were last time. That's not enough to solve real-life challenges. I mean, sometimes it could, but in many cases it's not enough. So let's warm up. We are going to have a little look at some data that we found in R. I'm going to show you in a sec. These are data, daily data on ozone concentrations, radiation, so it's kind of weather, environmental type data, wind speed, temperature, and then the day and month. So these are specifying exactly when the observations were made. So in a way there are 4 really observational variables, and then there are 2 variables coding for the time that these were recorded. So these are daily observations. Now let us dwell a little bit on this, and then I'll jump into R. This is just to show you that we found the data inside R. It's called air quality in the outset. Then we prepared the data a little bit. We did some data wrangling or whatever, data pre-processing. We did that for you because this is not a course in data wrangling, data handling, data pre-processing. But that is an important part of real-life data analysis and work with data to be able to handle and check and control and make sure that the real-life data that hits us comes in a meaningful sense. There could be missing values. Well, I just save us from that problem. I leave out those days where there are some missing values, just not to take that additional challenge into what we are going to discuss today. I actually also did a bit of pre-looking at the data. One of the ozone values were pretty extreme. Let me take that out of my data set in the outset already. And then let's check how the data actually looks. And let's go into R and do it. So here's the same lines. So here's the histogram of the raw ozone, because the task or the purpose of looking at these data would be to be interested in the ozone concentrations and potentially how those concentrations might depend on other things like temperature, wind speed, and so on. That's the kind of the setting and the problem that we are trying to learn about by looking at these data. This is pretty skewed data, right? So just to save us a little bit of problem later, I go on right away, and even though it's a bit premature compared to what I teach you, and we'll get to that at the end also, as I also say here, really, maybe I could or should wait to see how the behavior of the residuals, like I talked about last time, because it's really the residuals that should be nicely normal, not necessarily the raw data. So I'm a bit sort of doing something on the edge here compared to what we teach you, but hey, that's everyday work with the data. Maybe experience tells us when we have really skewed data like this, well, we know it's still going to look skewed on the residual. So anyway, to save us that process here, I right away define a new variable, which is the log of the ozone, right? So I'm going to focus on the log ozone by defining this new variable. Let's have a look at least again on the raw data. Would that look slightly more normal, even though I realize it's slightly silly because it's not really the residuals, but anyway, it looks maybe a little nicer at least. So anyway, then just to not, I'm just picking out a few of the columns, and I'm giving the columns my own names. Let's see if I already have my first. I should start all over because now I messed things up. Let's see. I define my own version of this one. Let's see, that was much better. Then let's see the kind of data structure that I now sort of created, a nice tidied up data for further analysis, which is a data frame of 110 daily observations of my focus of interest here, the log ozone, and I'm having temperature, wind, and radiation level as three potential explanatory variables, input variables, three potential x's in the explanation modeling of this y. I also have a time variable. Let's not dig into that. R comes with certain time variables and time formats that can be used if you manage how to use them. That's an example. We could look at the air data. It's just 110 times the number of columns like that. We could go head and we could go tail to first 5 and last 5. So now I have my data set that I'm going to look into. Let's have the first look. In this new world, there is a lot of nice functions in R to do nice graphics. And this is, again, you could take classes of data science that have a complete focus on how to actually tidy up data within R, how to do nice visualizations. Really nice courses, but we only have 5 points and 1 day to do MLR with you. So you're going to have to wait and do such courses later in your career. For now, let's look at this pairs. This is, yes, you can almost get the idea of a function called pairs. Let me make all pairs of scatter plots. And basically it puts in the smooth of the relation also. So here is basically the full pairwise plotting of those. Yeah, I already called them, there is a y maybe, and then 3 x's, and then there is the time. So down here in the bottom row, we have kind of the time development of all of the 4. The log ozone seems to be slightly increasing over time, over the time period that we are studying here. What about the relation between the log ozone and each of temperature, wind, and radiation? Can you follow the little arrow here as it goes down? Well, the top row here shows that there appears to be increasing ozone level with increasing temperature from a day to day. So days with high temperatures have high levels of ozone. Days with high wind tends to have lower values of ozone concentrations. days of high radiation tends to have higher, at least up to a certain point, then sort of it maybe drifts off again there. So maybe there's a bit of nonlinearity going on here. Maybe, or is it just random fluctuations? I'm not sure. Right? That's the kind of questions and insight that we will use regression modeling to look into. What's really the story about this? Well, this is a nice start just to look at the pairwise scatter plots. The challenge also that we'll get to at the end is that there could be relations not only between x and y, but potentially between different of the x's, maybe. Maybe two x's are related to each other also, and that creates an additional challenge, which basically is one of those challenges that most machine learning classes are dealing with. So that's the purpose of, one of the big purposes of machine learning is that's to deal with when we have too many x's in a way. And so, yeah, that's one of the challenges. So we could go back. This is all in a way recap of last time, just taking two variables at a time and looking at how the relation is. Maybe I use my R here to put in a smooth. I didn't give you the theory of smoothing, but I guess you can get the idea. It's something about making some kind of curve that matches data best possible. You have to take another class to learn about smoothing formally, but it's a nonlinear fit of the data, just depicting more or less the relation. The only relation I taught you was the linear regression last time, the fixed line. So we could go simple pairwise again to sort of just emphasize the type of scatter plot that we were looking at last time, where we just looked at ozone, which would be the log versions of ozone, as a function of temperature. And it seems pretty increasing, right? What about correlation? Guess the correlation? What's the correlation here? Any guesses? Just shout. 0.7? Good job. 0.74. Almost a copy of the one I've thrown in your faces a couple of times already. How much percentage of the log ozone values are explained by temperature? How much of the day-to-day difference variability in the log ozone can be explained purely by the temperature differences of days? Roughly 50%, right? Which is the square of the correlation from before, R squared. Good. Let's, and by the way, was this significant? This is a recap of last time. Is the temperature effect significant? Meaning, is there really a relation, sort of statistically, between the log ozone and the temperature? Yes, pretty convincingly. I mean, we don't know the size of it. Well, that's not true. We know the size of it. It's here. It's a bit difficult to interpret because it's on a log scale. But nevertheless, it's definitely, certainly a positive relation between temperature and the ozone concentrations from day to day here, right? Good. Just to make a point, what if we actually just put in complete noise? That's what I do here, just to make a silly point maybe, if you're already there. So here I just take a random normal numbers. I plot the ozone, and then the name is upside down here. Sorry about that. Should be the other way around because it's log ozone. Is that actually... No, actually, that's the, let's do, sorry about that, let's turn it around. I'd like to put in the noise as the Y and the temperature, Here we are. same plot, of course, basically, but with the right, now it's turned the right way. What would be the correlation be? I know it's a different one. Should be temperature then for this to make a point here, temperature. Not a big correlation, right? Just to say if there's no relation, there's no relation, what would the p-value be? Now we go here, noise, temperature. Now I'm getting stressed by time. There we are. Significance, no relation, of course. I mean, sorry for the silly point to make. If we simulate random numbers, we don't see any relation at all, of course, and that's how it should be. Good. So basically, I talked our way through all of this in the R setting. I used already what we were taught last time in doing a simple regression model, so let's not look more at that. I already did this with you in R, so that's a copy of what I just did, a recap of last time. We could also continue. Now I'm not going to do it, but we could, or maybe I'll do it. We could also take in the wind speed or the radiation separately, maybe, right? That would just do what I taught you last week a number of times. Do it for wind, do it for temperature, do it for radiation. What would that give to us? Let's just go and check. For instance. Here's ozone versus wind. Negative trend, negative coefficient, significant effect. Yes, there is a significant relation. What about radiation? Positive and extremely significant again. All three of them appears to influence ozone, right? So this is why we would like to take the next step and do them together, all of them. But we are going to play the usual game before we get to that. This is actually almost the best time of my week, these few seconds here. We seem to be almost there. Let's... still a few. Signing up. Here we go. Are you ready? Is it readable from the back? We're going to see a few of those. I'm sorry about that. So if we have a few places still in the front if you'd like to get closer for readability. Anyway, not too bad. A few of you picked the wrong. No, you picked the right p-value, but you made the wrong conclusion, right? The p-value was the one for the temperature, yes, but when it's above 5%, it's not significant. That by which we mean we couldn't prove a correlation for these data. I took a subset of the data where we didn't see a significant correlation on that subset. Good. Who started out? Rasasibel, or whatever. You're there.